Hello, my name is Chris Rizos from the School of Civil and Environmental Engineering, the University of New South Wales, Sydney, Australia. I'm a past president of the International Association of Geodesy and a former member of the governing board of the International GNSS Service. My presentation is entitled Geodesy, Precise Positioning and GNSS, the pillars supporting the geosciences. Let's start with the definition of geodesy. It's a science that uses a range of space technologies to make a variety of Earth system observations that contribute to our understanding of the dynamics of the solid Earth, the atmosphere, and the oceans. Hence, it's contributing really to all of the other geosciences. The most significant advances in geodesy can be traced back to the adoption of the US GPS by the civilian geodetic community in the early 1980s. Today, global navigation satellite systems, or GNSS, use the positioning principles first demonstrated by GPS. Hence, there is a continuity of space-based positioning capability for 40 years. There are over 100 GNSS satellites in orbit, providing improved GNSS geodesy performance. High accuracy, three-dimensional and four-dimensional absolute and relative positioning is one of the most important scientific capabilities provided by space-based technologies. And GNSS, starting with GPS, has revolutionized geodesy and the geoscientific disciplines that it serves. Precise GNSS positioning is extremely challenging. It requires special receiver hardware, complex ground infrastructure, and sophisticated measurement analysis software. But today, several services facilitate precise positioning. The International GNSS Service, or the IGS, has made possible sub-centimetre accurate positioning to support geodesy and the geosciences for almost 30 years. This slide shows the evolution of satellite geodesy and GNSS geodesy. And you can see that satellite geodesy effectively starts from the beginning of the space age. We have satellite-based positioning commencing shortly after that, and GNSS geodesy from the early 1980s right through to the present day, when we have all the other constellations being launched. The establishment of the IGS commenced in early 1990. This rather busy slide shows all of the aspects of the geosciences related to the dynamic Earth. And we can see that, in fact, monitoring of many of these phenomena can be done using GNSS. For example, we can look at the ionospheric structure and its dynamics using GNSS. We can look at surface winds and sea state using GNSS reflectometry. We can look at the shape and deformation of the Earth, of course, using GNSS. We can measure tropospheric water vapor distribution using, again, GNSS. And defining and maintaining the precise global reference frame in support of many of the other geoscience studies is also done using principally GNSS. Let's look at GNSS geodesy's capabilities and how they may be able to be applied to geoscience. The first class are what I might refer to as point kinematics in 3D and 4D. These are related to the motion of a single point due to plate tectonics, regional effects, and seismic impacts. There's also local deformation due to fault motion, landslip, volcano subsidence, etc. And as well as that, there's engineering monitoring. Second class of capabilities relate to platform trajectories. In this case, we can refer to, for example, georeferenced vehicles, aircraft, ships, and UAVs, mainly for mapping. And the second one is precise orbit determination of gravity, altimetry, remote sensing missions. Third class is remote sensing using ground and satellite-based GNSS receivers in support of meteorology, space weather, and GNSS reflectometry. Then there's also precise time transfer and metrology. In this presentation, I'll be focusing only on the first of these capabilities, the precise point positioning. GNSS Geodesy capability, point kinematics. There are two aspects to that. One is the measurement of crustal motion or ground and structural deformation through measuring changes in the coordinates of GNSS static receivers. The second is the definition and maintenance of terrestrial reference frames. These are necessary to ensure that these coordinate changes are in fact due to geophysical or engineering effects and not to datum instability. And for both of these we need permanent GNSS reference stations. We have GPS measurements collected since the 1980s which allow this coordinate continuity through time. That is, make it possible to do four-dimensional positioning. Next generation GNSS or multi-GNSS will improve coordinate accuracy and maintain this continuity. So, point kinematic measurement using GNSS can come together in this slide here as an example of the measurement of ground motion. Two types of ground motion. There's the very slow motion of the tectonic plates shown here in this slide of the order of a few centimeters per year. Also shown on this slide are the red epicenters of major earthquakes. And when an earthquake event occurs, that seismic motion can be the order of several meters. And really we have thousands, many thousands of permanent GNSS receivers which can track both the slow motion and the fast motion. The terrestrial reference frame that I was referring to earlier is the International Terrestrial Reference Frame, the ITRF. And it is the most precise global datum. And it allows us to measure continental drift, crustal motion, ground deformation, and seismic movement. The ITRF definition and maintenance is the responsibility of the International Earth Rotation and Reference Systems Service. And the ITRF is realized not only by GNSS, but really by permanent geodetic station coordinates and velocities that are determined from a combination of four space techniques. VLBI, very long baseline interferometry, SLR, satellite laser ranging, GNSS, and DORIS, microwave tracking station position solutions. But the connection to the ITRF is really via relative or absolute GNSS positioning techniques, and that way we have millions of ground marks and thousands of GNSS continuously operating reference stations that are now given ITRF coordinates. This slide summarizes the GNSS and RNSS. The number of satellites are shown here in brackets, and we can see the forward GNSS constellations, GPS, GLONASS, Galileo, and BEIDO. In fact, there are several generations of GPS and of GLONASS and BEIDO. The regional navigation satellite systems, of course, there's QZSS and the Indian regional navigation satellite systems. And by the year 2020, we had more or less full operational capability on almost all of the constellations. So we're now in an era of multi-GNSS, and for Geodesy this brings considerable advantages. We have many more satellites, so we have increased availability and improved geometry and ultimately improved accuracy, of course. Multiple constellations also improves robustness, particularly resilience against system failures, and multiple frequencies also substantially improves accuracy. This slide is courtesy of Jackson. It shows the visibility of GNSS and RNS satellites across the globe. We can see it is very high. That's in some parts of the world, particularly in South and East Asian regions, which we can refer to as the hotspot. We have more than 30, perhaps even more than 40 satellites visible at any one time, above an elevation angle of 30 degrees. On this slide we show the complex signal spectrums for the different GNSS and RNSS systems. We have multiple frequencies and multiple signals. And really the most complex and expensive GNSS receivers and antennas are used for precise positioning applications, especially for geodesy and geoscience, because we want them to track all, or at least most, of the broadcast signals. We also need extensive ground infrastructure of continuously operating reference stations, and supported by sophisticated measurement, modeling and analysis tools to compute these accurate coordinates. And this is really where we need services that are able to do this to support applications. The potential of GPS for geodesy was realized in the early 1980s and was used for many regional geodynamic studies. The International Association of Geodesy released an announcement of opportunity in 1991 for the establishment of the International GPS Service for Geodynamics, known as the IGS. And here we can see a map showing the rudimentary tracking network from 1993. After a 3-month test campaign in 1992, on the 1st of January 1994, the IAGS became an official service of the IAG. From 1999, it has been known simply as the International GPS Service, and in March 2005 was renamed the International GNSS Service. Today, over 500 permanent tracking stations comprise the IGS network, and the IGS has traditionally supported 2 GNSS, GPS and GLONASS. And new IGS efforts include tracking and analysis of Galileo, BeiDou and QZSS. This slide shows today's IGS Global Tracking Network. It consists of over 500 sites owned and operated by approximately 142 organizations located in about 45 countries. And many of these receiver sites are capable of tracking all of the GNSS constellations. The permanent stations come in different forms, different form factors. There may be pillars, there may be tripods all over the world. But what is important is that as many as possible of these are operated for long periods of time, for many years, so that we can get that coordinate continuity necessary for reference frame definition and maintenance, as well as for determining the products of the IGS. The IGS collects and archives the GNSS measurements from its global network in order to satisfy the objectives of a wide range of scientific and other high-end applications. For example, these data sets are used by the IGS to generate the following data products, which are all freely available on their website. We have the high accuracy GNSS satellite orbits, Earth rotation parameters, coordinates and velocities of the IGS tracking stations, GNSS and tracking station clock information, and timescale products, as well as ionospheric and tropospheric information, and of course the raw GNSS measurement files. This slide tries to summarize all of the components and outputs of the IGS. It's more than just the network. They're on the left-hand side. We have a governance structure. We obviously have an interface to thousands, many thousands of users. There are also working groups studying particular scientific problems related to GNSS, pilot projects and services. We have the online presence, and then ultimately the data products that are available through the data centers. And most importantly, we have multiple analysis centers which analyze the GNSS data to produce the various products. However, in a multi-GNSS world, the IGS will need to upgrade its network, receivers, its analysis center software, and products. But we must still rely on historic GPS measurement files to support the long-term four-dimensional geoscience studies that I referred to earlier. Summarized on this slide are the range of GNSS Geodesy applications. We see the ITRF maintenance is a very important one for Geodesy in the geosciences. The development of modern national geodetic datums and geospatial infrastructure. Disaster warning systems for earthquakes, tsunamis, landslides, volcanoes, and building deformation. For weather operations and climate studies, remote sensing and mapping, reflectometry, GNSS integrity monitoring, precise orbit determination, and others. So, in summary, we have GNSS providing a precise positioning capability, which through geodetic methodologies and geodetic services such as the IGS is able to provide support to the geosciences that are studying dynamic phenomenon on the surface of the Earth and its atmosphere and oceans that are related to changes in position of receivers, as well as the propagation of the signals through the atmosphere. Thank you for your attention. I hope you found this presentation of interest. Goodbye.